Is anybody out there? Hello? Hey,
Hello.
people. Hi, people. All right. So I will share my screen. Are we ready to rock? Give me just a minute. Actually, I need just a minute. Sorry. Okay. Okay, so today we're going to be talking about MRI, of course, and in particular image reconstruction. And we're going to try to get to two subjects. One's called parallel imaging and the other is compressed sensing. So I'm going to review the Fourier transform and some of its properties and a review of MR physics, and then finally parallel imaging and compressed sensing. So here's a Bohr atom model of the atom. So y'all are muted, I guess, but what does the Bohr model of an atom consist of? What does an atom have? What's in any atom? Anybody?
A nucleus.
Protons.
Good, nucleus. And the nucleus consists of protons and then some neutrons. And what else is missing here?
Orbiting electrons.
Yeah, orbiting electrons, right. And so this is a Bohr model of an atom. Here's a Bohr model of hydrogen. It's just one proton with a electron sort of rotating around it, orbiting around it. Did you guys see that little animation right there? Yeah, great. That took a lot of time. Glad you enjoyed that. The electron orbits the nucleus. That is a current, right? That an electron moving through space is current. And so it generates a magnetic field. And so this little atom becomes a tiny little magnet. And if you have a particle, which might consist of a bunch of hydrogen atoms, and in MRI, we typically think of a particle of water. So each water molecule has 2 hydrogen in it. Each atom is this tiny little magnetic vector because this electron's rotating around it. And typically, the magnetic vectors are oriented randomly. So like this. However, if you place this particle in a very large external magnetic field, then you get some preferential alignment with that external magnetic field. And that gives you a net magnetic vector in the direction of the external magnetic field. And this is what we measure. This is the signal that we typically get with MRI. An analogy that I like is if you take a whole bunch of compasses and put them in a dryer while the dryer's spinning around, the compasses will preferentially align with the Earth's external magnetic field, but not much, right? Not much. And it turns out with water, we see about the size of that little arrow that extends beyond the sphere is about 1 in every 1 million hydrogen atoms. That's the size of that signal. We get about 1 part per million. So it's a very small signal. Okay, so we define a coordinate system centered on this particle. And then there comes Bloch's equation. So have you all seen Bloch's equations before? Yeah, okay. So, and perhaps you've talked about relaxation and recovery. We're going to ignore that for today. We're just going to look at the other part of Bloch's equations. And Bloch's equation has this parameter in it, this gamma. It's called the gyromagnetic ratio. For hydrogen, it's about 43 megahertz per Tesla. And so if you have a 1.5 Tesla magnet, which is a common strength for an MRI, then you're looking at about 64 megahertz is the base frequency of your signal. And what this does, these Bloch's equations dictate a precession. And so the magnetic vector, if it were somehow in the XY plane, would be precessing around the external magnetic field. And it's precessing according to the left-hand rule, not the right-hand rule, the left-hand rule. That confuses everyone. It's just the other hand, right? And so what happens is, you know, if I place a coil nearby now, we've got basically a little magnet that's rotating. And so that little rotating magnet is going to generate a voltage in the nearby coil. And that's what we measure with MRI, is this voltage across the terminal of a nearby coil because of these little rotating magnets. That's our signal. And then the frequency of precession is called the Larmor frequency. By the way, good exercise. Try to see in your own mind why this is rotating according to the left-hand rule rather than the right-hand rule. Go back to Bloch's equations and see if you could figure it out. Okay, so this standard frequency at which it's rotating is the Larmor frequency. And like I said, for water in a 1.5 Tesla magnet, it's 64 megahertz. Okay, so this vector is rotating at 64 megahertz in the lab frame. And then, like I said, the changing magnetic field induces a voltage in the nearby MRI coils, and that's what we measure. We can consider a separate coordinate system, one that rotates with the particle, so 64 megahertz. And in this separate coordinate system, what's going to happen? Can someone describe it to me? What do you think is going to happen if we were to, you know, look at this separate coordinate system, if we were to isolate it in its own graph? Well, the answer is obvious. I'm going to assume you all are just too lazy to unhit mute. What happens is that the vector is stationary, right? Because the coordinate system is rotating with the vector at 64 megahertz. So the magnetic vector is no longer rotating around. And so these coordinate systems have names. The one on the left is called the lab frame. It's the coordinate system that's sort of centered on the MRI machine. And the one on the right is called the rotating frame. And we can always just bounce back and forth given the amount of time that's elapsed. Because we have 64 megahertz, that's 64 million cycles per second. So if we know 1 second has elapsed, it's rotated around 64 million times. And so it's like we deleted the external magnetic field in the rotating frame. It's like that B naught is gone. Because recall the rotating frequency is gamma times the magnetic field. And since it's no longer rotating, it's like there's no external magnetic field. We'll only consider the rotating frame from now on because it makes everything super nice. So, you know, one way to do rotations, like if I tell you rotations, you've got two elements, right? X and Y. How would you rotate this vector? How do you rotate a vector? You know, think back through all the classes you've taken. How do you rotate a vector? Just go ahead and spit it out there. You've got a vector. You need to rotate it. What do?
By a rotation matrix?
Came through for all of you. So you could do it with matrices, right? You could rotate a vector with matrices. But now you got to deal with matrices. Alternatively, you can represent, since it's only 2 elements, you can represent your vector as a complex number. So rather than a vector of 2 elements, mx, my, you could just have a complex number where mx is the real part and my is the imaginary part. And then the nice part about that is, how do you do rotations with complex numbers? How do you rotate a complex number? Anybody know? If you want to rotate by theta, how do you rotate? You multiply by e to the I theta. That's what complex multiplication is. Complex multiplication is you multiply the magnitudes and you add the angles. And the magnitude of e to the I theta is 1. Okay, so the magnitude is going to be unchanged. And you're going to add the angle. You're going to rotate the vector by theta. So we've taken, once you start multiplying with complex numbers, you no longer need to worry about matrices. You just use the natural multiplication that's embedded in the algebra of the complex numbers. Okay, so B0 is this giant magnetic field. It's always on. And what's happening is underneath this plastic cover of the bore, the patient goes into this bore on this little bed, and underneath the plastic cover are like miles and miles of coil. And they're superconducting wires. So the machines typically use liquid helium to cool down the wires down to superconducting levels, and then they pass current through, and that's how you get your external magnetic field. And like I say, you place the patient on the table, and then you shove them into the bore, and you know, in very small periods of time, the water in the patient, all the hydrogen atoms will have aligned with the external magnetic field, like less than a second. And at that point, a patient is just a piece of meat and all they do is complain. Silly patients. And we can alter the magnetic field, right? There's this constant magnetic field that's on. But the magic of MRI is that we can change the magnetic field as a function of space. So also inside that plastic shell are these coils here. They're called gradient coils. And they let us change how strong the magnetic field is as a function of space. And these are called gradient coils. You'll see why in a second. So the patient's in the bore. And you know, we've got this lab frame that's centered on the patient. Typically Z, you know, goes out their head, right? X is to the right and Y is out the patient's front. This is assuming their feet first in the bore, face up. Okay, so these gradient coils change the Z component of the magnetic field as a function of space. So here is that magnetic field. It's in the lab frame, in the rotating frame. So we don't have the B naught as before. And what we have is just the Z field is going to be X times the GX value plus Y times the GY value plus Z times the GZ value. And so if GY and GZ are off, and let's say GX is 1, then the Z field is going to go up to the right and down to the left of the patient. So we're changing the external magnetic field as a function of space with these gradient coils. So in this example now, GX and GY will be off and GZ will be on. That's the Z prime direction. Here I've got 3 different particles. And you see the red arrows, you know, at the very center, because Z prime is 0, there is no external magnetic field. So in the rotating frame, that arrow is not going to move. As you go higher in Z, since GZ prime is positive, it is going to move. And this vector is going to rotate according to a left-handed sense around the Z vector pointed up. So it looks like this. You see what happened? The magnetic vectors rotate because of the gradient field. Now, actually in the world frame, in the lab frame, they're all rotating at 64 megahertz plus this amount. But since we're demodulating by that 64 megahertz, we're taking it away. So all we see are these like small rotations. And if we turn these gradient fields on for a little while and then we turn them off, we see that these vectors are now stationary in the lab frame, but at different phases. They each have a different phase. They have a different angle. An angle for a complex number is its phase. And so what we've done is we've encoded something about the position of each. And so, like I said, we've got these little magnets rotating around. And so precessing magnetization in the XY plane induces a voltage in the receiver coil. Because they're rotating around and there's a coil nearby, it's going to generate a coil. That's just fundamental physics. So we've got, at location XY, we've got the jth particle, it's got a volume delta Vj, and it's got a phase phi j. That's what's happening here. And the coil doesn't see just one particle, right? It sees them all. And the total voltage that's gonna be generated is the sum of the contributions from all of these little particles. Okay, so that's what this sum is. We're summing over all the particles. Are y'all keeping up? Any questions? Okay, so now I'm going to take the limit as the volume goes to 0. Do you guys know what happens? What happens to this expression as I take the limit as the volume goes to 0? Think about that. I'm going to get a soda. Anyone just shout it out. What happens to a sum when you take the integral? Oh, I just told you. When you take the limit as the volume goes to 0, a sum becomes an integral, right? That's the definition of the integral. And so that's all that's going to happen here. Oh, sorry. By the way, we know an expression for the phase, right? Because the frequency is the magnetic field times the gyromagnetic ratio gamma, right? And phase is just frequency times time. So, for any location, we've got, R dot G. So this dot here actually means the dot product. So for the particle J, it's at location R prime. It's going to be dotted with whatever the gradient field it is at that location. That's the magnetic field that it sees. So its frequency is going to be gamma times that, and we're going to integrate that over the time that we have the gradient field on for. So that's its phase. Then I'm going to take the limit, assuming the particles don't move, and taking the limit as the particle size goes to 0, we end up with this expression here. Okay. So now, rather than having mxyj, a summation of p particles over the index j, we now have an integral over space, mxy of r prime. And so this coil is seeing all the particles, it's summing up all of the particles, it's all an integration is, right? It's a summation. It's summing up all of the particles in their phases. And that's going to be the signal that the coil sees. It's going to be proportional to that. This is just recopying the expression from the last slide. Okay, now I'm going to define a new variable. Kx prime is going to equal gamma over 2 pi times the integral of g. And similarly for y and z. So I'm going to have this k vector. It's a 3-element vector, kx, ky, kz. And with this definition of k, I can now change the above expression into this one. What is this? Do you guys recognize this expression? What is this? This is the fundamental equation of engineering. This is fueled engineering for generations. What is this? Any ideas? This is the Fourier transform. So that's all an MRI is. That's what an MRI machine is. An MRI machine is something that takes the Fourier transform of U. And at every point in time, we get one value in the Fourier domain. This is not isolated to MRI. X-ray, CAT scans, radar, optics, they all magically come down to the Fourier transform. And so what the game of MRI is, we're going to manipulate these gradient fields, right? The gradient fields dictate which values in the Fourier domain we're going to get. We're going to manipulate them to get different values in the Fourier domain. And then we're going to try and make a picture from the values in the Fourier domain that we have. That's how you make pictures with MRI. So, you know, you might think of sheet music, for those of you that are musicians, like you might think of sheet music as a code of how to play whatever instrument. So I'm used to piano. So you look at the notes and the notes tell you which keys to hit at which time. This is the sheet music of the MRI instrument that I'm about to show you. So each of these lines, it's not nearly as many keys as the piano, right? It's more like a trumpet where you have, we actually have just 4 sort of tones: RF, GX, GY, GZ. Forget about RF. And then DAQ means that's when I'm going to acquire data. So either on or off. I either acquire data or I don't. And what happens is when we first excite with the RF pulse, when we first excite, we create this probe in the Fourier domain. And if we don't do anything, the probe is located at the 0 frequency. Then we're going to turn on some gradient fields. In this example, I'm going to turn on the GX. I'm going to make GX negative and GY positive. So the probe goes to the left and up. And then I'm going to turn GX on positive for a while. And this is when I'm going to acquire data. I'm going to acquire data the whole time that GX is positive. And that gives me one line in K-space. That gives me one line of Fourier values. And it's not really a line, right? It's a set of points along a line. We have just a finite set of points along a line. So if you're a mathematician, the set of samples has measure 0, right? It's just a finite set of isolated points. And then we repeat the process. But each time we're going to change the amount of GY. And this gives us a set of lines in K-space, a set of points in K-space. And conventionally, these points are on a 2-dimensional grid. Given that, how do you think you make an image if you have a set of points in the Fourier domain on a 2-dimensional grid? Any ideas? If you have a grid of Fourier values, how do you make an image? Forget images. If you have, let's talk about sound. Let's say somehow you have some sound wave, and for some reason you have a set of Fourier values in the spectrum of the sound wave, in the Fourier domain of the sound wave. How do you get back the sound wave? How do you get an estimate of it? Big hint, it starts with inverse. How do you get, we have samples in the Fourier domain and we want our sound function. We're going to do an inverse. Okay, we're going to use a
Inverse Fourier
computer.
transform.
Say it again.
Inverse Fourier transform.
Close. Good guess. It has a lot of words that I like. It has inverse, it has Fourier, and it has transform. The issue is that the inverse Fourier transform is the integral, and it can't be done with a computer. So what is the closest a computer can get to that? The answer is the inverse discrete Fourier transform. And the way you think of a discrete Fourier transform is the approximation to a Fourier transform that you can make with a computer. So that's what you do. That's what MRI is. If you collect all of this data, then you just perform an inverse discrete Fourier transform to make your image. Okay, I forgot a tool. I need a tool. I'll be right back. Any questions on that? Why do you think the signal is proportional to that integral of particles rather than equal? Any ideas? Why is the signal just proportional rather than equal? Let's say you're building an MRI machine, right? And so you're like, oh, neat, I'm going to generate a voltage on this coil. And I'm going to record them. And I'm going to have values in K space. Why is it? So what I'm talking about is this point here, right? This is approximately equal to, but it's actually proportional. The signal is proportional to this. Why is it proportional rather than equal? Let's say you're actually going to record values with a computer. What do you have to do to that coil that's generating voltage? How do you get, we've got like a coil with a little hole in it, right? And so there's going to be voltage here, and we want to get this voltage into a computer.
Because
What do we attach? What's that?
Because we will like record digital signal, so it will be sampled in time.
And how do you do that?
And
What do you
not
have?
continuous.
Right. And what do you have to add onto the coil in order to get those digital samples?
Mm. You mean like physically?
Yeah, physically. This device has a name.
An ADC?
Yeah, an
Converter.
analog to digital converter. And that thing has a constant that we don't know. It has a bias. So Natalia, you were oh so close. You guys did it. Okay. So here is one of my favorite images. It was my buddy Bake. He's dead now. May he rest in peace. His name is Bacon. So this is an image, and this is almost what a two-dimensional Fourier transform of this image looks like. Why am I saying almost? Like, what is it? can this not be the Fourier transform of this? The answer is because the Fourier transform is complex. Complex necessarily means for each location we have two values. But I'm only showing you one. So this is the magnitude of the Fourier transform of this image, okay? It's a real image. There are some nice symmetry properties, in particular the Fourier transform of a real function is real and even. So now what I'm gonna do is show you one sinusoid. That is the most significant sinusoid in this picture. That is the sinusoid for the largest Fourier coefficient in the Fourier transform of this picture, okay? And now what I'm gonna do is go about adding one sinusoid at a time. And we'll see what that looks like. So I'm adding the sinusoid on the right, and the sum of all the sinusoids is this picture on the left. So this is what Fourier, now I'm adding 10 at a time, but you sort of get the point. This is what Fourier realized. He realized that any function can be made as a sum of sinusoids, of complex sinusoids. Can you imagine how much that must have blown his mind? He was like trying to figure out how heat dissipates in metal. And so what he, like, look, we're at 6,000 points in. We're at 6,000 points in the picture with 1,000,000 values. And we can see it very well. Like we're done, right? We're done. So that's what MRI is. We go through K-space, we go through the Fourier domain, we collect one value at a time, and then we add all of those up in just the right way to make the image, right? Okay. So I have this website, nicholasdwork.com. That's my name. You can ask Faye. And then I have this tab here called teaching. And here I have the MRI signal equation video. And this is a video presentation of the lecture that I just gave you, if you want to go through it again later. Okay. So there's an issue that I didn't tell you about. Here's the coil, right? And let's consider two particles of water of the same size. They have the same amount of water, these two particles, 1 and 2, okay? Which one's gonna give me the stronger signal? Any ideas? The closer one, right? The closer you are to the coil. So 1 presents a much stronger signal than 2. if you somehow rotate a magnet in the coil itself, that typically creates the strongest signal, right? Try it at home, shock yourself. See which one gives you the better shock. So that's kind of a joke, but actually the first person to discover Kirchhoff's voltage law, the sensor he used was his arms, and he shocked himself, and he sort of sensed how far up his arms he could feel the shock for different voltages. And then he never published his results though, because he thought everything was trivial. And so then, Kirchhoff invents Kirchhoff's voltage law. But Maxwell learns about this method that this guy invented. And so one day the university president shows up, in Maxwell's physics classroom, and they're all shocking themselves with batteries and measuring how far up their arms. Like, oh my God, you can't do that with students. But he could. Anyways, so there's this map, right? If I were to draw a contour plot of the sensitivity of this coil, it would go like this. Roughly, right? Roughly. This is a contour plot, right? So like you sometimes see contour plots with maps and elevation, where this is the highest point and this is the lowest point of the map. Same thing, right? This is the most sensitive region. And this is less sensitive. And so the reason this is significant is because the signal equation now, this is what I wrote before, right? I forgot what I wrote. Well, can someone tell me if this is right? I think this is right. This is what I wrote before, right? So we're integrating over a volume and summing up the sizes of these particles and their phases. But now you know, the farther away from the coil, the less it senses. So it's like there's this other function superimposed. And this function rho is called the sensitivity map of the coil. And so this is, the signal we measure is not the Fourier transform of the object. It's the Fourier transform of the object times the sensitivity map evaluated at K of t. So let's say you take this picture, right? And so because the coil gets less sensitive as it's further away, the image is going to get darker as you get further away. And this is what that looks like. So here's an image. We used 8 coils to take a picture of a knee. And you can see, like this coil, the third from the left on the top, you can see the coil was right at the back of the knee, right? So it's very sensitive to the tissue at the back of the knee, and it gets darker as it gets farther away, right? And similarly, the coil at the bottom on the right the coil is right at the kneecap, right? And so it senses the front of the knee very well, but it gets darker as it gets further away. So let's say you take this picture and you want to like undo that to some extent, right? So, you know, we have these Fourier values, we take the inverse discrete Fourier transform, and it turns out that our estimate of the image, right, is not what we want. It's not, oh, I should say this. Our estimate of the image is not MXY. It's actually like rho times MXY, and I should say approximately here. So what if we really did want an estimate of MXY? What could we do? We want MXY, but we have rho MXY. So what can we do? I think y'all are thinking too much. Just spout out the first thing that comes to mind. Like you've got MXY and you got rho MXY and you want MXY. What do you do? Okay, suppose you knew rho, right? Suppose you knew rho. Then you have rho MXY, you want MXY, what do you do?
Divide by rho.
Yes! Way to go, Natalia, dynamite drop in. To get a better estimate, divide by rho. But then that leaves us the question, how do we get rho? How do we get this sensitivity map? Any ideas? What would you do? Let's say I actually gave you an MRI machine, right? It's this giant machine. It costs $1,000 an hour. I've allocated a technician to you, so that's going to be even more money. And I said, you know, brilliant student of Peter's, I need a sensitivity map, and I've given you all the tools you need to go get one. Get me a sensitivity map of the coil. How do you do that?
So I would do like multiple measurements between like two fixed points. I'm just guessing, and then like subtract one from another, like inverse, square, low, all this stuff.
Very good, very good,
Yeah.
very good.
And figure
You
out
could do
draw.
that. You could do that. That'll work, and we'll get to that in a second. But there's a much simpler way. What if MXY was 1? And what does it mean for MXY to be 1? It means it's just a constant. So what you do is you go down to the store and you buy one of those jugs of Arrowhead water, right? And now you know that the thing is the uniform. It's a uniform sample everywhere. And so you shove that in to the machine and you take a picture of that. And the picture is not going to be uniform, right? It's going to get darker as it goes farther away from the image, of the coil, sorry. Guess what? That's the sensitivity map. So note that. So how much programming did I just save you, Natalia? You were going to go off and spend a week doing programming. That if MXY is approximately equal to 1, then, you know, after we do our inverse discrete Fourier transform, this is approximately equal to rho. And actually, for a special case of medical imaging called hyperpolarized imaging that my lab works on, one of the students just did exactly this. He put a bottle of water in the machine, took a picture of it, measured the sensitivity map, then used that sensitivity map to correct the MRI images by dividing, and found that we can better diagnose cancer because he did this. Of course we can, right? Of course we can. We'd have to. That's what's happening. His name is Philip Lee, by the way, to give credit where credit is due. Okay, so I've been calling them coils, but they're actually antennas. They're pieces of wire that sense electromagnetic signals and generate voltages. That's what an antenna is. They're antennas. And they've got this spatial sensitivity, right? And let's say we wanted to make better images, right? How could we make better images? How could you change the machine to make better images, do you think? If we go back over here, like, how could we make better images?
Use more coils.
Yeah, right, yeah. You add more antennas. More information will give you, more information is always better. So for example, if we have C coils, capital C coils, then like a simple, quick and dirty way to get an estimate of your image is to sum over all your coils. The individual estimate of each coil, square it, and then take the square root of that. Okay, so this is called like square root sum of squares reconstruction. And so if we do that, for this example over here, I've got 8 coils. If I do this, take each of these images, square them, sum it up, and take the square root, I get this, right? So you can see this is better than any one of these images, right? You see both the kneecap and the back of the knee and what's inside. And what's happening is like, this one's brighter over here, and this one's sort of brighter over here, and this one's kind of brighter in the middle, same with this thing. So they're all compensating each other. And when you sum them up together, you get this image. And so for the longest time, it was the job of coil engineers to make coils so that when you summed them up in just this way, it would give you the most accurate representation possible.
Can I ask a quick question here?
Absolutely.
So, yeah, so basically, like, if we have, I don't know, if we would place those coils like in a wrong way and then apply this square root something, we'll get like really nasty images with like bright spots and
They're
or-
never, I hear what you're saying, And the answer is kinda, yeah, right. Yeah, that happens. But it's never nasty, right? It's just not great.
Mm-hmm.
The coils are not such that, because there's electromagnetic effects where if you place two coils too close together, then they start to like couple. And then their sensitivity maps are no longer the superposition of the individual sensitivity maps. And so you never get this phenomenon where you get this super bright spot.
Okay,
The
yeah.
coils kind of naturally compensate for that.
Got it.
And the other thing is that when the coil engineers were still making coils to do this, they would place them in rigid structures. And so there was you couldn't like bend the coils. There was nothing like that.
Mm-hmm.
Okay. So so this is quick and dirty, and if you have a bunch of coils, but look, we have more information, right? We have multiple sensors, but we have multiple sensors. We should not need as much data. I actually have really nice handwriting, just not with this tablet. We should not need as much data. And so this is the idea. Of parallel imaging. It's the worst name on earth. I call it multi-coil imaging because that's actually what it is. There's nothing parallel about it. It should be called multi-coil imaging. And actually, if you go back to the original papers, it got the name parallel from something that the authors were confused by. They're confused by what was happening, and they thought something was happening in parallel. It actually wasn't happening in parallel. There's nothing parallel about it. It's called parallel imaging now. And so, okay, so what's going to happen here? We have C sensitivity maps. And so what is the model, right? We have our image, M. Well, I'll just call it M from now on. And in fact, you know what, because I'm lazy, I'm going to call it little m. This is our image, okay? And what happens to this image? Well, this sensitivity map gets imposed, right? And we'll think about just the first coil. And then it gets Fourier transformed. So we'll approximate that with the discrete Fourier transform. And then this is, proportional, approximately equal to our first set of data, right? And this is true for all coils. So we can find them by minimizing we're going to sum over all the coils the discrete Fourier transform times the sensitivity map of the coil times M minus the actual data we have. And we're going to take the L2 norm of that squared. The L2 norm is just the Euclidean norm, right? So like Pythagorean theorem, but in higher dimensions. X1 squared, or B1 squared plus B2 squared plus B3 squared plus B4 squared plus dot 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 plus Bn squared square rooted. That's the L2 norm. And then we're going to take the square of that, and it gets rid of this square. So if you have one equation and 4 unknowns, you're screwed, right? Totally screwed. If you have 4 equations and 4 unknowns, unless things are magically bad, you can solve for your unknowns, right? And what happens is, what's happened is, for every point in K-space now, rather than getting 1 equation, we get 2 if we have 2 coils. We get 1 value from one coil and 1 value from another. And so we can get half, if we have 2 coils, we can get half the data and still have enough equations for the number of unknowns that we have. This is called sense. So the guy that invented this is named Prusman. And like, you know, he's very famous. This is used all the time. So it has a problem. You need to know the sensitivity maps. And your estimate of the sensitivity map is directly related to how well you're going to be able to image how good your picture is going to be. But if you know your sensitivity maps, you can formulate this optimization problem, and then you can estimate your image well. It doesn't come for free. The less data you collect, the less time you spend scanning, the more noise you're going to have. But it comes like, typically there's so much water in our body that even though we only see 1 part per million, we have way more signal than we need. And so you can dramatically reduce the scan time and collect your images with parallel imaging. And so I wasn't being flippant. It's about $1,000 an hour in the scanner. It's a $2 million machine. You're going to take a technician, and when a patient shows up, they're going to sit in there an hour. That's typically how long it takes. And we want to vary the parameters of the scans in order to see different contrasts. So you've been learning about T1, T2, right? Yeah. So we want to see different contrasts and BSSFP, and we want to watch the heart move and all sorts of stuff. So the less time you can spend per scan, the more information you can get about your patient, the more diagnostic the doctor is going to be able to be. The better comprehension the doctor will have of the patient. So parallel imaging was huge. It was huge. It has an interesting history because, like I say, the first paper got it wrong, got part of it wrong, and they called it parallel for a wrong reason. And so they published it, and everyone had so much fun harping on the author for how wrong he was on part of the paper, that no one paid attention for like a decade to the fact that he could make great images in half the time. And so it took about a decade before this really took off because they just said way too much in their paper. Okay. So far, we've used just physics, right? We've used just physics. And what we're about to do is step our toe into data science. Should we take a break? Should we take like a 5-minute break? Let's do that. Let's take a 5-minute break and I'll see you here at 1:36. Is anyone back? Anyone? All right, some people. Just a second, let me get reset up here. Okay. Any questions on what we've covered so far? Faye, what are you dying to ask? I caught you with food in your mouth. Ha. Do you guys know that
Actually,
Faye
I have
images
a
lungs?
I have a question actually.
Yeah, let's hear it.
So when you were telling me that it costs $1,000 an hour, it got me thinking about just healthcare in general. But I guess I could wait until the end of class to ask this if we're on a
Okay.
time crunch.
Yeah, let's wait till the end.
Okay,
right.
sounds good.
Okay, so far we've used physics. But we're gonna dip our toe, like I said, into data science. And what that means is we're gonna use information about our image like that we already know. You already come in with knowledge about what your thing is gonna look like. Any idea what sort of information that'll be? What do we already know about our picture? Any ideas? Here's a simple one. No matter what you put in the machine, it can never have a value of infinity. So that's good. That doesn't really help us, but at least that's something, right? Do you have any other ideas? Like what sort of information do we already know about our image before we even know anything about the part of the body or where we're going to scan or what age the person is or anything like that? What do we already know about our image?
The MXY is always positive.
It's not, it's complex. In general, it's complex. But you might say it's okay, so Faye's landed on something great here. It is complex, but you might think it's real. Perhaps the thing you're putting into the body is real. It turns out it's not real, but it does have low phase for interesting reasons. The phase is small. So what you can do, there's this trick where you collect a very small amount of data to estimate the phase, and then you can pretend it's real. And you can collect only half of the data because the Fourier transform of a real function is real and even. Since it's even, you only need half, right? And this is called homodyne imaging. So that's a perfect example, right? Faye realized something about the image that we already know, and we were able to use it to reduce the amount of data that we need. Anything else? You know, a common assumption made of data is that it's band limited. It means you don't have a frequencies, you don't have high energy and high frequencies, right? What does an image that is high energy and high frequencies look like? What does that look like? Do y'all know? If I give you an image that's got nothing in the low frequencies, but is high intensity and high frequencies, what does that look like?
Really bright.
No. Do
Really
you,
dark.
do y'all remember? Go ahead.
Said really dark.
Good guess. Do y'all remember what they used to call snow on TVs? Like if you didn't connect this, it looks like this. This is what an image of high energy and high frequencies and no energy and low frequencies looks like. Now, can any part of the body ever be like this? Can any part of the body ever look like this? The answer is no. You'll never take an MRI image, get this out and say to yourself, that's a good image. If you get this out of an MRI machine, you say to yourself, my goodness, I have a bug in my code. Like things are terrible and I need a break. Okay, so one that was identified recently is particularly interesting. So there's another transform called the wavelet transform, right? So here's our picture of Bacon again. May he rest in peace. He was a lovely dog. And now what I'm going to do is take the wavelet transform of this picture. And when I do that, I get this. This is the wavelet transform of Bacon, right? This is the wavelet transform. And what do you notice about this picture? This one over here, like what's the first thing that jumps out at you? If I were to ask a 6-year-old to describe this picture, what would the 6-year-old say?
Edge detection.
Yeah, definitely. And that's what's happening here. This is detecting vertical edges over here. This is detecting horizontal edges, and this is detecting diagonal edges. And in particular, and then this is the low frequencies in the upper left corner, approximately, right? Approximately. So, and then what do you notice? What do you notice about this picture? Like if you ask a 6-year-old, you know, to describe this picture, what is he going to say? He or she?
It's really dark.
Yeah! Were you the same guy that answered dark before I can't see your face?
No, I think that was Banu.
Oh, Banu, this was your moment. This was your moment to shine. But yeah, thank you. Yeah, this is dark. It's dark, right? Dark means 0 in a picture. So most of the wavelet transform of our image is 0, right? Let's say we wanted even more zeros in this picture. How could we get them? What could I do to get even more zeros here? Any ideas? Well, we got a lot of zeros by taking the wavelet transform of Bacon. What can we do? One thing I can do is just set all the values to 0, but then I can't recover my image, right? I want more zeros, but I want to be able to recover my image. So what can I do?
Can you do wavelet one more time on the?
Yeah, you can do
left
wavelet
portion?
one more time, just on the upper left-hand corner this time. And when I do that, I get this. Right? Even more zeros now. Lots more. And this is always the case. No matter what natural image you take, if you compute the wavelet transform, you're going to end up with almost zeros. And if we want even more, we can do it again. Right? So here we have lots of zeros now. Lots of zeros. And this has been exploited forever. It's been exploited for forever in compression. JPEG 2000 is basically compute the wavelet transform of your image, set lots of values to 0, and only send the non-zero values. That's what JPEG 2000 compression is. And now what we want to do is try to exploit this property, but on the other side. With compression, you capture the whole image, and then you do some sort of function that reduces the amount of data, and then you send the reduced data over your channel, right? Now we want to exploit this property to capture even less data. And so the way that's done is, so first some notation. For a vector x, the L0 penalty is the number of non-zero elements. Okay? And what some brilliant people realized, if you know Mickey Lustig, he was working with a professor named Donahoe, and they largely figured it out. Because it was Mickey Lustig, it got transferred over to MRI, and now it's everywhere. And then Terence Tao with Candes proved how well it works. So Candes was from Stanford and Tao was from UCLA. And they met at UCLA at something called the Institute for Pure and Applied Mathematics. And so they proved that it's correct. And so what was realized is that we can represent the image very well by some estimate x hat, where the L0 penalty of the wavelet transform of x hat is small. Now, this is not physics, right? We come in with this preconceived notion that this is true. It is true, but there's no proof that this is the case. We just, they just noticed that with natural images, this is the case. So it's a phenomenon, it's phenomenological rather than physical. It's data science. Okay, so we have our model. Don't forget our model. I'm gonna forget about the sensitivity maps for now. So we have our image. We're gonna take the Fourier transform of it. But then I'm gonna apply a mask, D. And this should approximately equal our data. D is a data sampling mask. So I forgot to include it in the parallel imaging portion, but it should have been there as well. So, you know, D is 1 wherever we collected data in K-domain and 0 everywhere else. Okay? And so to recover our image, we're going to solve the following optimization problem. We're going to minimize DFM minus B squared subject to the wavelet transform of M is less than some integer Z. Okay? So we're only going to give ourselves Z wavelet coefficients. And we're going to say they could be whatever value we want. You only get Z of them. You could use any ones you want. And then I want the data to match, right? I want the data to match. And so how do you solve this? One answer is we cannot solve this. This is called an NP-hard problem. And humans don't have a good way to solve a problem like this. But we've got a trick that does pretty well, okay? We got a trick that does pretty well. First, what if I didn't have this constraint? I just wanted to minimize, you know, MFD is B. Can we make this 0? It turns out we can, right? So consider DFM equals B. This linear system, this system of linear equations it has more unknowns than equations. What does that tell us? If we have more unknowns than we have equations, how many solutions are there to our system of equations? If you've got 3 unknowns and 2 equations, typically how many solutions do you have? Okay, if you've got two unknowns in one equation, how many solutions are there to this system? I've got one equation and two unknowns. How many solutions are there? Anybody? What if I took out the 2? What if it was just x plus y equals 8? Well, if y is 1, then x could be 7, and that's a solution. And if y is 2, x can be 6. And if y is 3, x can be 5. And if y is 4, then x can be 4. And if y is 4.5, then x can be 3.5. How many solutions are there?
Infinite.
Yeah, we have an infinite number of solutions. When we have fewer equations than we have unknowns, there are an infinite number of solutions. And in particular, we can satisfy this system exactly. So how do we do that? Well, we take the values of our data, right? Basically, we zero fill. In the Fourier domain, we put the values that we know where they are, and we set everything else to 0, right? And then we inverse Fourier transform. So if we zero fill the Fourier data, then we satisfy the system exactly. Do we have to zero fill? What if I like 1 filled? Would that still satisfy the system exactly? Do you guys understand what's going on? I'll draw another picture. So here's, a rectangular portion of the Fourier domain. And I collect data here and here and here and here and here and here and here. And that leaves all the rest of the data unknown, right? I've collected just these few data points, and that leaves all the rest of the data unknown. If I put 0 everywhere, right? Then I inverse Fourier transform that to get an estimate of m, right? So my first estimate is going to be the inverse Fourier transform of this, the 2D inverse Fourier transform, right? So I'm going to take so then what happens? Well, when I take the Fourier transform of that, it cancels out. That gives me back this, right? Then D is going to isolate just those points that I collected, and they're going to be exactly B, because those are the values that I put in there, right? This is called zero filling. And if I did 1 filling, it would be the same, right? And so this leads us to our solution. So we toggle back and forth between, we alternate between compute Fourier transform, and set known values. So for all of those values that we know, we set them to the values that we know. If we know frequency 0 is 5, then we compute the Fourier transform of our estimate, and we set 0 to 5. And if we know frequency 10 is 3, we set 10 to 3. You see? We compute the Fourier transform, and we set the known values. Then, inverse Fourier and wavelet transform. Set the smallest n minus r. We want only r values to be non-zero. So we're going to set all the rest of the values to 0. Then inverse wavelet transform. Okay, so you start out with some estimate. Let's say it's all zeros. You compute the Fourier transform and you set your known values to the values that you collected from the machine. Great. Now we've satisfied our data. You inverse Fourier transform and then you wavelet Fourier transform. And in the wavelet domain, you set the smallest n minus r values to 0. Then you inverse wavelet transform. You compute the Fourier transform, set your known Fourier values, inverse Fourier transform, compute the wavelet transform, set the smallest wavelet coefficients to 0, inverse wavelet transform. And you just keep toggling between those two. And this, absolutely amazingly, with about 1/3 of the data, this recovers the image perfectly. Not approximately, perfectly. And so this just, you know, you can see why it changed the world. Like, it's changed everything perfectly. But I could do a little better. So this is called compressed sensing. And you'll get to do it in your homework. Any questions on this?
Yes. So when are you doing this? Are you doing this immediately, like during the scan, or is this like a post
This
processing
is,
thing?
it depends on what you mean. So this is all post-processing. This is post-processing.
Okay.
But typically the post-processing, we really want it to be done in close to real time. Because what will happen is the technician will scan and they want to see the picture to make sure nothing went wrong before they take the patient out and send them home. And if it takes too long to gather the data, to reconstruct the image, too frequently they'll have to call the patient back and to get imaged again. And that's a real problem.
Okay.
So, but you'll see it doesn't take very long. You know, you do it for like 1,000 iterations. It takes no time on modern computers.
Very cool.
Do you guys have other questions? So look. Well, that's the lecture.
I think I have one.
Nice.
So as far as I understood this, I'm not sure I kind of like completely understood this, but I think we were talking about like sampling in previous lectures, and we said that there is like Nyquist theorem when we should like
Right.
take like at least like 2 samples.
Right.
Yeah, and so this thing allows us to do like even fewer.
About 1/3 as many.
Wow.
Yeah, you can see why it blew people's minds. And if you read the paper, there's this beautiful paper by Candes called An Introduction to Compressive Sampling. And the paper starts out like, we're all so surprised.
And are there, I think what I didn't get is, are there any limitations? Like, say I want to compress like all this way back, like to this 1/8.
I'm sorry?
I mean, are there any limitations?
Oh, of course. Well, what do you mean by that?
I think we haven't done any kind of like sophisticated data analysis yet during this course, but what I saw like in the like our previous homework, we had like a half of K-space data, and
Okay.
we reconstructed images, and it was like 2 images and 1 image, and we just reconstructed by just like mirroring the K-space, which is like conjugate filling. The simplest thing.
Yeah, okay.
Yeah, how is it called?
Well, I mean, you're assuming your image is real there.
Yeah,
So they gave you a real image. So,
yeah.
okay.
Um,
So but what do you mean by limitations?
I think I'm just trying to see should like, oh, so basically we have a real image. I mean, we have a signal, right? I think I'm just trying to understand is what I'm trying to understand is, are we just like take these samples right after we have this like ADC converter?
Yeah.
And we can just take just like that small samples. We don't need any kind of like initial bigger sample.
No.
Okay, so it's just like math. It's pure math.
Yeah, pure math.
Cool. Yeah, I was like, how is it possible?
Right. Yeah, I know. So I've skipped over, you know, there's a whole body of literature on this now, like tens of thousands of very deep papers. For example, you know, I said with about 1/3 of the data, the reconstruction is perfect. That's approximately true. The real answer is with about 1/3 of the data, the reconstruction is probably perfect. They proved it probabilistically. And there's you know, there's all sorts of literature on this. So, but this is definitely the gist. Any questions about anything? There was a student who wanted to ask about the cost of something.
Oh yeah, that was me. Here, I'll turn my camera on for that face-to-face interaction. Yeah, so you were saying it costs $1,000 for an hour?
Right?
So I'm guessing based on that, then imaging kind of like takes up a big portion of overall healthcare costs.
I mean, it depends, but okay.
I mean, I feel like it's a pretty important factor in like diagnosing, right?
Again, it depends, but okay. So what's the question?
Yeah, so like I mean, I was just thinking about, you know, universal healthcare, and I thought that was a pretty good idea, you know, like everybody gets to be treated. But then I recently saw that in Canada, that it literally takes up to like 11 weeks to get your MRI taken because there's a long wait list.
Right.
So I'm wondering, like, wouldn't that cause problems? And
Oh yeah. Like you know, the mortality rate due to cancer in Canada and in England is much higher than in the US because they have to wait to get scanned because it's universal, right? And the government pays for
yeah,
everything. The infant mortality rate, if you consider, so people are fond of saying that the infant mortality rate in the US is higher than in other countries. But that's only because in the US they consider a viable infant much earlier. So in England and Canada, where they have so-called universal basic income or universal health care, if an infant is questionable, they're more likely to call it a stillbirth than in America. And so for this, if you consider the same gestational age, right? All babies after 30 weeks, for example, the infant mortality rate in America is much lower than in other countries. I mean,
does
the list goes
stillbirth
on and on.
does stillbirth mean the baby is like not breathing or not
Not
crying?
viable, not viable.
Okay. Yeah, I just thought it was some food for thought.
Any other questions? Guys, it's been my pleasure. When you're cursing the creator of your homework, know that you're cursing me, and it makes my soul laugh. All right. See ya.
Thank you.
Thank you.
Thank
For
you,
sure, for sure.
Nick.
Bye.